Hello. This lecture material is going to cover basics of classical test theory and parallel forms. And this is the second lecture in the scale development module. So to begin, remember I've mentioned classical test theory in passing several times, and I've also included this formula right here where I've talked about the variances with respect to the way classical test theory views them. So we have observed score variance. That's the variability that we have in our data for a particular measure. And that is equal, in this case, what it is it's defined by this thing called true score variance. And true score variance is the variance that is attributable to what we expect in sampling variability for the true score. That is the score without that's pure, and we never have any access to that whatsoever. And then there's error variance. So when you combine true score variance and error variance, you get the observed score variance. Now remember, I said to you before that variance is the keys to the kingdom. When you understand variance and you understand that variance is something that's part of all of statistical formulas, and it's really the stuff that our uncertainty and quantification of our uncertainty relies heavily upon. So classical test theory is no exception to that, and classical test theory is based upon this really simple formula. I always suggest that students come up with some sort of brief word, and I like rote, R-O-T-E. So if you remember that classical test theory is just rote knowledge, the R is, I guess, silent. Observed equals true plus error. So that's the basis for classical test theory. And then Fred Lord was a pioneer in psychometrics and among many things. But one of the things that he suggested was that the logic of reliability as an estimate should be a ratio of variances, much like ratio of variances are part of, as I said before, all of statistical procedures. But in this one, it follows suit with the idea behind classical test theory, that you have true score variability and observed score variability. And remember that observed score variability is nothing but true score variance plus error variance. So this definition, rho, and later on you're going to see it as R, but rho is what we consider to be the parameter that we wish to estimate given samples. So reliability is a ratio of variances of true score variance over observed score variance. Now you'll notice that true score variance over observed score variance, that this could actually be simplified or actually made more complicated, but simplified for our purposes, where we could take the observed score variance and just substitute it for true plus error. So if you have true plus error, you'll see that as the error variance increases, our reliability decreases. And this is a really good way to think about reliability. Reliability is a property, as I emphasized during lecture, it's a property of the interaction between the person and the instrument, or the sample and the instrument. Reliability is not a property of an instrument alone. So it has to do with the sample and how the sample responds to the items within your instrument. And so this is a ratio of variances, just as there are a lot of other ratios of variances. Next, to expand the idea of reliability, and really to get you to understand what reliability means, the Green Book, but also many other psychometric texts, lead this very standard way of thinking about classical test theory, and it begins with parallel measures. So what we want to know is, we always want to know what the true score variance is, simply because if we understand what the true score variance is, and we're always going to be able to estimate the observed score variability. But by understanding parallel measures or parallel forms, we get a good sense of how to estimate reliability, Okay. And what you're going to learn from this brief review is that reliability isn't a single number. It's many numbers that you use to express different aspects of the dependability or the stability of the estimates for a given instrument that's been administered to a sample. So we begin with parallel measures, and parallel measures are defined by a pretty simple set of equations. And these equations, remember that statistics is largely not math, it's a language. But I'm going to use the equation that you're already familiar with, the rote equation, observed equals true score plus error, and I'm going to create one for two measures, measure 1 and measure 2. And the most important thing here is that our true score variances are equal and our error variances are equal. And when we have that, we then have that our observed score variances are equal. Now, this is the definition of parallel measures. And the reason why we want to be able to establish this really simple idea of parallel measures is in many cases, we wish to have parallel measures. We would like to have two measures that produce the same amount of variance estimates from our data. And remember, our data are the subjects or the sample by item interactions. And thus, we can make inferences about the true score variance and the error variance. So when would we actually have these two parallel forms? Well, we have them for ETS. ETS, when you take the GREs, you'll take a set of items that may be different than your classmates. And the reason for that is the item content isn't as important necessarily as the item difficulty. So ETS has devised this method of adaptive testing, creating parallel forms where they just place you along a continuum, but all of the true score variability and observed score variability, and therefore error variance, can be assumed to be equal. And those parallel forms are incredibly useful by reducing subject burden, your burden, by having to take all of the items, and also to be able to produce scores that are equivalent. So those parallel forms are useful. Okay, I'm going to stop here because this is the beginning of the next step that I want to expand upon the different ideas about reliability. So stay tuned for part 2.